Okay, good morning, everyone. Hope you're well. We are, believe it or not, nearing the end of the semester. Last week we finished off robots that can adapt like animals, where we looked at the map elites algorithm and the IT and E algorithm. That lecture concluded our discussion of solutions to the reality gap problem. As I mentioned last time, we're a little behind where I'd like to be at this point in the semester. So I've grayed out some lectures that I usually teach. If you're interested, they're now optional lectures. You can go and click on them, and the lecture slides and readings are available as usual. We finished our discussion of crossing the reality gap, which means we also finished our theme on open challenges in the field. I misspoke. We have one remaining lecture to look at in this theme, which we'll look at today. One of the open challenges, which you are now all intimately familiar with, is it takes a while for one person to set up a simulator, a robot, a neural network, a fitness function, an evolutionary algorithm to start training and evolving robots. If we would like our toy robots in our toy physics engines to eventually become more complex and more sophisticated and more capable, we're going to have more and more complex simulation environments, more and more simulations, more and more people building simulations, or at least collectively guiding the evolutionary trajectory of our robots. So we're going to talk about actually an ongoing project in my lab called Twitch Plays Robotics Today, which is an attempt to lower the barrier to entry to allow more and more experts to collectively evolve more and more robots. We'll talk about that today. And then on Thursday, we'll move into a actually a three-part lecture. Hopefully we have time for this. A three-part lecture on collective robotics. Up till now, we've been mainly looking at one robot operating alone. A lot of the tasks that we would like our robots to carry out are beyond the ability of any one robot. So under what conditions might we want to send a group of simpler robots rather than one complex robot? And if we do want to send a swarm, how do we go about evolving behaviors for it? I know some of you are trying to tackle this in your final project. Okay, so that's where we are, and that's where we're going in terms of lectures. You are continuing on with your final project. You are starting in today on deliverable 3. Hopefully most of you managed to submit a second weekly deliverable last night. Next Tuesday, May the 4th, when you submit, just after you've submitted your deliverable 3, I will talk about the final project and what you're going to be doing from May the 4th for 2 weeks until we meet for the last time on Monday, May 17th for the final project oral presentations. Okay. Any questions about the deliverables before we push on? No? Okay, one thing I wanted to share with you was a very nice result that one of your fellow students sent me this morning, Robbie Beatty, who Robbie I think is here this morning, who's been able to parameterize the quadruped to turn it into an N-legged robot. Obviously, as you can see in the picture here, in order to make this happen, you need to be able to specify not just the position of each of the links that make up the robot, but the orientation of the limbs as well. A couple of you have asked me about that before, so I wanted to just show you how you can do this. I haven't had a chance to write this up in the tips and tricks Reddit page yet, but I will try and carve out some time today to actually do that. But just to show you how this works, if you navigate to origin, inside the Pyrosim directory, there's a file called origin URDF. The URDF means this is obviously a part of Pyrosim that deals with writing out the URDF files. And origin is going to be the origin of the link as you describe it in the URDF file. I don't expect you to remember all this morning. I'm recording the lecture. You can go back and watch this at your leisure. So if you open origin urdf.py, you'll notice this particular class has a constructor. And inside this constructor, it writes a string It saves a string, actually. It writes it later, but that's fine. This string corresponds to a link in the URDF file. You pass into this particular class the position of the link, and the orientation by default has a roll of 0, a pitch of 0, and a yaw of 0. You can change this, for example, to instead write out a roll, pitch, and yaw of your own, and pass that in as a new argument to the constructor. If I compile and run my code now, I should get an error because I've added this argument. To origin URDF, but wherever that origin.urdf is called, it's missing that argument. So I've made this change where now you can pass in the orientation of an object defined by its roll, its pitch, and its yaw. If you go back and look at the error here, it'll tell you that it's this file that's complaining. So you go open up that file, go to that line, and add RPY, or roll, pitch, and yaw, as an argument to that call, which, as you see here, is send cube. And now in solution.py, where you generate the body, you can now send in a roll, pitch, and yaw of your own. 30 degrees, 0, 0. I can't remember if roll, pitch, and yaw is in radians or degrees. Robbie, do you remember offhand? Okay. Well, we can check that later. That's fine. Okay, so that's how you expose orientation of links to your code if you're interested. Okay. Any questions about the final project? Oh, I'm sorry, there was a question in here. Robbie says no. It doesn't remember. That's fine. We'll figure that out later. I'll add it to tips and tricks, and we'll go from there. Okay, so back to lecture. We're going to dive in now to this issue of opening up the scalability of evolutionary robotics. Just to set the stage for today's lecture, if we would like to invite into the field of evolutionary robotics large numbers of non-experts, we can't expect all of them will be willing and able, or have the time or the interest or the attention span to go through the Ludobots Reddit course and teach themselves physics engines and neural networks and fitness functions and all the rest. So how do we go about lowering the barrier to entry? The idea behind the Twitch Plays Robotics project is we're going to lower the barrier to entry by allowing people to interact with robots using the same method that we communicate with other humans, which is natural language. Why did natural language evolve? It's an interesting question in and of itself, but tangential to this course. One of the nice things about language, obviously, is it allows us to exchange a lot of information. And assuming we have a teacher-student or parent-child or master-apprentice relationship, the teacher or the caregiver may give some instruction that guides the way in which the learner learns, or in our case, provide some natural language, which is going to guide the way that a population of robots evolves. So this lecture, although it's really about trying to scale up evolutionary robotics, as you'll see, this is mostly about language. Throughout this course, we've approached the idea of building intelligence into robots not by trying to define exactly what we mean by intelligence and building that into robots. We haven't done that because no one has yet been able to come up with a precise enough definition of intelligence that we could program it into machines. So instead, we try and build in or evolve the building blocks of intelligence into robots. We've seen planning, theory of mind, self, non-self discrimination, active categorical perception, selective attention, you name it, a whole bunch of different building blocks. One of the most important building blocks, at least for human intelligence, is natural language. And we haven't talked about that yet until today. So I'm going to start this lecture. This is actually a set of lecture notes from a talk I gave a couple of years ago, as you can see here, about this project, about the Twitch Plays Robotics project. You'll notice scalable is in the title of the talk. So we're still trying to scale this up by inviting in large numbers of non-experts. But I mentioned here something called the symbol grounding problem. The symbol grounding problem is an idea that comes from philosophy, which is about language, and it's about why it's very difficult to teach machines language. So we're going to allow non-experts to try and teach and guide robots using language, but how do we get language into machines in the first place? That's already difficult. Let's start with the Chinese room problem. Hopefully most of you remember the Chinese room. We talked about this towards the beginning of the semester. The Chinese room, in a way, there's a lot of things that are kind of odd about the Chinese room. One of the things that's odd about the Chinese room is you could, or you might, choose to argue that the Chinese room understands Mandarin. The Chinese room problem was set up by the philosopher John Searle to make it seem that it seems like it understands Mandarin, but does it really understand Mandarin? And we had an interesting discussion about that at the beginning of the semester, which we won't repeat today. Let's at least look at how the Chinese room manipulates language. Let's use the word manipulate rather than understand. The Chinese room receives as input a bunch of squiggles and squaggles. It doesn't know the ideograms of Mandarin or Chinese, but it knows that if it sees these squiggles and squaggles, it should replace them on another piece of paper with another set of squiggles and squaggles. Imagine that I wanted to teach you, or you wanted to learn Egyptian hieroglyphs. But the only thing you had available to learn Egyptian hieroglyphs was an Egyptian hieroglyph dictionary written in hieroglyphs. So if you see some hieroglyph and you want to know what it means, you go to your hieroglyphics dictionary, you look up that symbol, and the definition of that symbol is written in a bunch of other hieroglyphs. By definition, you don't know Egyptian hieroglyphics, so you have to go look up each of those symbols elsewhere in the dictionary, which in turn is defined by another set of symbols. You go look up those symbols, and you go around in the dictionary forever. The only way you quote unquote understand any particular hieroglyphic is that it is equivalent to a bunch of other hieroglyphics, which is the definition. The Chinese room problem is very much like that. The Chinese room does not understand any one hieroglyphic or any one ideogram in Chinese. It only knows that this ideogram is related to these other ideograms in a certain way. There's some web of interrelationships between symbols, either hieroglyphics or ideograms in Chinese. But is that really understanding? If all you can do is go round and round and round, you never ground those symbols anywhere. They're floating in air, and there's something about that idea that that's a way to understand language that's unsatisfying to a lot of people. So that's where the symbol grounding problem comes from. How do you get a machine? By definition, a machine doesn't understand language. If you give it a bunch of squiggles and squaggles, which are English characters, and you just tell it that these squaggles are related to these other squaggles, if you give it an English to English dictionary, how does a machine ever ground these symbols? How does it ever understand the relationship between these symbols and the real world? We want to try and ground symbols in the real world for a machine. Okay. Maybe this is abstract philosophy. Maybe it doesn't matter. It turns out that a lot of AI at the moment is continuing to try and is A lot of AI projects like the Cyc Project, which is still going to this day, basically feeds in huge amounts of text to machines and tries to teach machines that, for example, this particular symbol, Bill Clinton, is related to this symbol, United States President, using this symbol, ISA. Tree the plant is a generalization of this thing. So this symbol is related to this symbol according to this symbol. This symbol is related to this symbol according to this symbol, and so on. This is the Cyc Project. Cyc is meant to be short for encyclopedic knowledge. So the Professor Lanaut, who's been running this project for 40 years, is hoping that this will allow Cyc, the machine, to wake up and be all knowledgeable, at least given everything that's in Wikipedia or on the internet. Another unfortunate way to interpret the title of this project is that it's cyclical. It does not ground these symbols. Does a machine understand BILLCLINTON if the machine only knows that it's ISA, UNIT, and so on? Is that really an understanding of language? How do we go about getting a machine to ground symbols in the soil of the real world? Nobody knows, and this is another reason why this lecture is included in the open challenges in robotics. Okay, I'm going to skip over a couple slides here. How do we go about solving the symbol grounding problem? Well, there are hints. There are a growing number of hints coming from our understanding of how humans ground the symbols of language in our everyday experience. We do not learn language by reading dictionaries of dictionaries. However we go about learning language, there is some deep connection between the language that we're learning and its relationship with the real world. But what is that relationship exactly? Let me show you some hints that suggest what that relationship between language and physical experience is. I think we mentioned the motor strip before. Can someone just type into chat, yes or no? Did we talk about the motor homunculus here, the motor strip? I talk about it from time to time in lecture. I don't remember if we've talked about it here. Does anybody remember a discussion about the motor strip? I don't see anything in chat, so I'm going to assume we haven't talked about the motor strip before. Okay, the part of your brain that would be covered if you're wearing earmuffs, right across here, this is known as the motor strip. We haven't talked about this. Okay, great. So it's very interesting. If you put someone in an fMRI scanner, a brain scanner, and you focus the scan on this part of the brain and you touch someone's index finger, a particular part of the motor strip will light up. If you touch a nearby body part like the middle finger, a nearby part of the motor strip will light up. If you start by touching parts of the subject's body from the head down to their toes as they're in the scanner, you will notice a series of lights lighting up along the motor strip. So this contorted human body here, this is known as the motor homunculus, or the little man inside the motor strip. And it's interesting that the arrangement of the human body, or nearby body parts, are related to nearby parts of the motor strip. You'll notice in this picture of the homunculus, some parts of the body are larger than others. Why do you think that's the case? It wasn't drawn like that by accident. There's a reason why some parts of the homunculus are drawn larger than smaller. What do you think they are? They have more, Hannah says they have more sensor neurons. Close. Missy says more nerves to control these body parts. Much closer. As we all know, your tongue is much more sensitive than your back. You can feel, if you're sitting in a chair, you can feel the chair pressing against your back, but localizing exactly where something is touching on your back is hard to do. So as Hannah is also correct, you have a lot more sensory, you have a lot more sensor neurons distributed through certain parts of your body than others, so that if you touch slightly different parts of the tongue takes up much more real estate in the motor strip than your back does. There are a couple of body parts that are not drawn on the motor homunculus here, which actually take up a huge amount of real estate in the motor strip. You can probably figure out what those body parts are. Okay. What does the motor strip and the homunculus have to do with language? This seems like something that has completely nothing to do with language. But one of the most interesting things I think that's recently been discovered in neuroscience over the last 10 years is there is a very deep relationship between the motor strip and language. In this particular study carried out in 2010, they placed human subjects in a brain scanner. They asked the subjects to just relax, not think about anything in particular. And then people just read fiction. They read novels to these subjects. And as they did, so the subjects were just listening to English words. As they did, they focused the scan on the motor strip. So we're looking down on the brain. You can see here's the motor strip here. What they found is that words that were associated with particular parts of the body caused those parts of the body in the motor strip to light up. For example, when the subjects heard the word talk and lick, these two words were picked because they sound similar. They sound similar, but obviously both of these words have to do with the mouth. The mouth or the face part of the motor homunculus would light up. Two other words, grasp and pick. They picked grasp and pick, also lit up arm-related parts of the motor homunculus. Walk and kick, which have to do with the legs, light up the blue part of the motor homunculus. If you can kind of do this experiment yourself, if you just kind of relax, and unfortunately you're going to have to keep listening to my voice. But when I say the words talk and lick, for most of you, you become a little bit more aware of your mouth. When I say the word grasp and pick, you become a little bit more aware of your hands. For most of you, when I say grasp and pick, you become a little bit more aware of your dominant hand. Righties will feel their right hand a little bit more than their left. Lefties will feel their left hand a little bit more than their right. When I say walk, kick, run, you will tend to become a little bit more aware of your legs. This is all subjective, but that's usually a good indication that those parts of your motor strip are lighting up. You'll notice that three of the words here, lick, pick, and kick, these were chosen deliberately because they sound very similar to one another, but they do not light up close parts of the brain. So you could imagine that words that sound similar, lick, pick, kick, should light up similar parts of the brain, and words that sound different, talk, grasp, pick, would light up different parts of the brain. That's not the spatial relationship, or doesn't seem to be the spatial relationship. Words are more related in the brain, or where they light up in the brain, based on which parts of the body those words tend to be associated with. So we're going to talk about these special kinds of words today, which are motoric words. These are words or verbs that are very specific to parts of the body. They're a symbol, so talk and lick and grasp and pick, these are four different symbols, but they seem somehow intuitively to be quote unquote closer to physical experience, in this case, closer to parts of our body. So this is giving us some hints about how to ground symbols in a robot's physical experience, which is to use the body as the linking piece between language and the outside world. Language, outside world, body. Body seems to be, at least for humans, part of the story. Okay. This is something we're just starting to learn more about in neuroscience. I'm sure there's lots more of the story to be learned. Let's jump to another literature, which is the literature of linguistics. For those of you that are interested in language and linguistics, I cannot recommend George Lakoff enough. He's written a number of wonderful books about the nature of language, and specifically embodied language. We've talked about embodied cognition in this course quite a bit. What is the relationship between language and the body? George has a wonderful book. He's got many wonderful books. My favorite is Metaphors We Live By. Metaphors, like don't jump to conclusion or don't look back in anger, these are aspects of language that seem very abstract. Metaphor is an abstraction, is one of the more abstract parts of language, it seems. But certain metaphors are what Professor Lakoff refers to as embodied metaphors. And you can see why. I've picked two metaphors from the English language here, and each of them have motoric words hidden inside of them. Jump, for most of us, makes you aware of your legs. Looking back is an interesting one. What is it about looking back? Don't look back in anger. What does this metaphor mean? If you look back over your shoulder, obviously you don't see your anger behind you. What does it mean? What's the meaning of this metaphor? If you have an idea, you can go ahead and type it into chat. If you want to unmute yourself and offer an opinion, that's fine too. Henry says this metaphor is about remembering something from the past, right? So the past or time is not mentioned in this metaphor. This is one of the beautiful things about metaphor. There's a lot that's unsaid or hidden in a metaphor. So we're searching this metaphor for the hidden meaning. Why is looking back associated with the past? This is the key to understanding this particular metaphor. If I turn around and look behind me right now, I'm not going to see my past. I'm going to see the white wall behind me. Why is looking back? Why is that associated with the past?
I guess we associate time as like a two-dimensional line, and we look back as in where we were.
That's it exactly, Henry, right? So when we look back, we associated that with where we were. So now we're no longer talking about time, we're talking about space, where we were, our position in space. The more you meditate on the metaphor, don't look back in anger, the more levels of meaning there are hidden in this metaphor. Human beings are primary, as Alex says, we think of time as linear, moving forward into the future, right? Why is forward associated with future and why is back associated with the past? It turns out that in most human cultures, that association holds true. If it's true across cultures, it usually means that this particular association, forward equals future, back equals past, that is something that doesn't have to do with culture. It has to do with something deeper and older, which in this case is human physiology itself. Our primary sensory apparatus is vision. We are looking forward. And most of the time, we're walking forward. So when you're walking forward, whatever you see in front of you is about to become your future because you're walking or moving towards it. If you turn and look back, whatever you see is in your past. If human beings tended to walk backwards more often than we walked forward, this metaphor, this association between forward in the future and back in the past would seem non-intuitive. I don't know if there's any non-native English speakers on the call this morning, but this is something that's kind of interesting. When you're learning a second language and you start to learn their metaphors, You can ask someone who's learning these metaphors to explain it to you without giving them a definition. And most non-native English speakers, if they have enough English under their belt, they can tell you, they can infer or puzzle out the meaning of this metaphor without you having to tell them. The reason they can do so is because most everyone, regardless of your culture, because our eyes face forward and we tend to walk forward, whatever is in front of us is our future, and whatever is behind us is in our past. So without realizing it, most of us use metaphors or understand metaphors or communicate with a hidden code. And that code, or that decryption and encryption device, is the body itself. We all share bodily experiences just based on the way our bodies are built. And we use that to translate from one language to another, or from language to experience, or from abstract metaphors and back again. So we're going to play a game now for a moment. Hopefully you get the idea now of what an embodied metaphor is. Embodied metaphors hide motoric words that are the keys to unlocking the meaning of those metaphors. There are many of them in English. I've played this game on and off over the years with my students. I've heard hundreds, maybe thousands of embodied metaphors by now. If you can think of some more, go ahead and type them into chat. Don't hold back. Let your fingers do the walking. Don't tie yourself up in knots thinking too hard. I'm sure you'll be able to puzzle this out. Takes a while to get going, but once you warm up, you should have no trouble being able to piece together some embodied metaphors. Running out of time, that's a good one. Yeah. My hands are tied. That's a great one. You're starting to get the hang of this. I'm looking forward to seeing what other embodied metaphors you come up with. Falling in love, that's a great one. That one usually comes up. Spinning your wheels, that's a good one. You all seem to be warming up. Your tongues are becoming loosened, or your typing fingers are becoming loosened. The subject matter is heavy. Aha, heavy and light. Very good. Spinning your wheels, obviously that's not quite about our body, but clearly that's an embodied metaphor. To chill out, yeah, that's a good one. I'm not going to take this lying down. I'm going to wait until I hear some more. I am titanium. That's a good one. I hadn't heard that one before, but I think that qualifies. Isn't there another pop song? I'm bulletproof. Yep, that's a great embodied metaphor. Couple more and then we'll move on. Are you running out of ideas? Okay, so hold your horses. All right, yes, hold your horses, everyone. Let's push on. So two different pieces of evidence coming from two different literatures, linguistics and neuroscience, that the body somehow is an intermediary. It allows us to ground the symbols of language or ground abstract metaphors in felt experience. And that allows us to not go around and round in circles, but to ground symbols in felt experience. Seems that that's how humans do it, or this is part of the story for how we understand language. How do we take these ideas and build them into machines? Here's the idea. Imagine we have a hypothetical robot, and this robot has pressure sensors on its feet, not unlike the robots you're working with. And over time, as the robot is behaving and moving around in its environment, from time to time, just based on how it's moving, maybe all 4 of its feet happen to come off the ground, and at that time, all 4 pressure signals or all 4 touch signals in the feet drop to 0. The robot can sense this value, or you can think of 4 curves here if you want. The robot senses how pressure is changing. Imagine we give this robot an ear, and in that ear, from time to time, the robot notices a relationship. Whenever all 4 touch sensors drop to 0, the ear hears the following, JUMP. The robot does not understand language. All it knows is whenever this happens, whenever the sensor values drop to 0, someone or something out there says JUMP. If we turned around and we asked the robot, JUMP question mark, we give it this additional squiggle, and we tell the robot whenever it sees this squiggle, that means tell us what JUMP means. If we were to feed in JUMP question mark, the robot would do that. So the robot cannot speak yet. The robot can only listen. The robot would show us that it understands JUMP by jumping. Even though this is a very simple robot, and this is just one single motoric symbol from the English language, jump, if a robot was able to show us what jump means, the robot has already grounded at least one symbol. It is not learning what jump is by looking up jump in an English dictionary and seeing a whole bunch of other English squiggles which define what jump is. As you're going to see in a moment, we can get a robot to actually do this, or a bunch of non-experts are going to get a robot to do this. That's the Twitch Plays Robotics project, which we'll spend the next 40 minutes talking about. But before we get to Twitch Plays Robotics, admittedly, it's a simple project. The robots only understand a few motoric symbols. And from now on, when I use the word understand, what I mean is that the robot has detected a relationship between its own felt experience. There is some unique signature of its sensor values that correlates with a symbol. People or something emits the symbol JUMP whenever this sensory signature is generated by the robot. So if the robot, now this is the hypothesis, if the robot can ground motoric symbols in felt experience, could a more sophisticated robot start grounding increasingly abstract words, increasingly less motoric words? Could it ground them in more motoric words? Let's consider this symbol here, MOVEMENT. The robot might notice that this symbol, it hears this symbol more often and for a wider range of sensory patterns. This symbol appears for a much more specific set of patterns when all 4 touch sensors go to 0. But the robot might notice that this symbol appears whenever the touch sensor values change. If the touch sensor values stay the same, then it doesn't hear this symbol. So the robot might learn to ground this symbol in its own felt experience, this symbol in its own felt experience, but the robot might also learn that because this symbol spans a wider range of sensory signatures for the robot, maybe there's another word, maybe the robot comes up with this word, a new symbol, and this symbol says, this symbol is associated with a wider range of my experiences than this one is. So now the robot is starting to build what's known as a semantic web, where the web, as you can see, the nodes in the web are symbols, and the edges between nodes in the web are labeled with other symbols that represent relationships, semantic relationships between words. leading to a semantic web, but leading to a semantic web in a very different way from the Cyc Project, which is just digesting text from the web and looking for relationships between symbols. So they're both projects are trying to build a semantic web, an understanding of language. One does it in a non-embodied way. The other, robot in this case, does it through its own body. It's interesting to think about how far we could push this process. If a robot can ground jump in felt experience and movement in jump, could a robot understand political movement as a type of movement? Could it understand socialism as a type of political movement? Seems difficult. Let's take not socialism, but a different word, capitalism. Capitalism. Let's go with democracy. Democracy seems like a very non-motoric word. It is very abstract. However, thinking about thinking is misleading, as always. If you think about the word democracy, there is a motoric association you can imagine. There is a way you might be able to ground the word democracy, not just in these abstract words, but in felt experience itself. What is the felt experience of democracy? Seems almost like a oxymoron. Can't be true. What does democracy sometimes feel like? Any ideas? Anyone played tug of war before? You take a very long, thick rope. You have 5 people on one side, 5 on the other, and both are pulling. Sometimes one group is pulling a little bit more than the other. There's collective action by 2 groups, at least in this country, 2 major groups that are pulling in opposite directions. Democracy, in a way, obviously this is a bit of a stretch, often feels like tug of war. Okay. Anyways, this is sort of the big vision. We'll see how far we get. Let's come back down to earth. Let's ground our discussion. I'm going to slip some embodied metaphors through this lecture, see if you can find them all. Let's reground our discussion in just symbol grounding of motoric words. Okay, so let's talk about Twitch Plays Robotics now, which is an attempt to do this. The project itself has 4 phases. We'll see how many of these phases we get through today. Most of you, I think, know about Twitch TV already. It's a big website where you can go and watch other people play video games or cook dinner. There's a live video stream, and you can comment in real time in chat next to the video stream with the other observers of the stream or with the streamer themselves. There is a set of channels called Twitch Plays where what you type into chat influences what happens in the stream. Twitch Plays Robotics is a project we set up. It's a particular Twitch channel where what you type into chat influences what the robots do. Twitch Plays Robotics is an ongoing project. I stream it from home because of the pandemic, and I have to turn it off when we have lectures. So Twitch Plays Robotics is turned off at the moment, but about a half an hour after lecture, you can navigate to Twitch TV/Twitch Plays Robotics, and you can try it yourself. Okay, so let's start with part 1 of the project, which is action. In the action phase, we're going to start up a physics engine with a virtual robot in it, exactly like what you have. In this case, however, instead of evolving populations of robots, we're going to play one virtual robot over and over again in sequence. And every time we do, we're going to drop a random neural network controller into that robot. And the resulting random actions, we're going to stream to Twitch. So I will show you a video of this. This was Twitch version 1.0. We're now up to Twitch TPR 4.0, but this will give you the basic idea. There's a lot going on in this video, so I'll play it a couple times. You can see the video stream on the left, and you can see on the right, at this particular time, we had about 30 viewers, and they were all talking to the robot. We'll talk about the chat in a moment. As I mentioned, each time we run this, we have a different virtual robot, and it's being controlled by a different random controller. In a moment here, we're just going to skip ahead here a little bit. Okay, every once in a while, we tell the crowd that we have just told the robot walk forward. We tell the crowd that to think of these robots as pets. They don't understand English, but they may be able to respond to a small set of commands, but we don't know what those commands are. And it's the Twitch crowd's job to teach these robots language. So in essence, we're going to try and recruit the crowd to help this robot ground various symbols. The crowd can do this in two different ways. The crowd can propose which symbols to ground, which motoric words should we try and teach this robot. And then once we do, we're going to help them understand the relationship between that symbol or that word and the robot's own felt experience. At this particular point in time, the crowd has typed in walk forward a bunch of times, as you can see on the right here. So this is the crowd voting for the word that they want to try and teach the robot next. Every 5 minutes, we switch what the crowd can teach the robot. If you look in the top right here, you'll notice people voting for different commands. We don't make the commands as the investigators. It's up to the users to decide which motoric words, which commands they think they can teach the robot. And you'll notice that the votes for walk forward are winning at this point. And so in a moment, the command WALK space FORWARD is going to be issued to the robot. So here we go. So the violet robot is now hearing the term walk forward. And so now the second task of the crowd is to tell the robot whether it is obeying this command or not. So the crowd is being instructed to type into chat VY if yes, the violet robot is walking forward. So violet robot, yes, you're walking forward. If you do not think that the violet robot is walking forward, type in VN, which is violet robot, no, I don't think you're walking forward. You'll notice 2 people just voted no, that the violet robot is not walking forward. 4 votes, the violet robot is not walking forward. So at the previous moment here, we had 4 votes that this violet robot is not walking forward, and no votes that the robot, 0 votes that the violet robot is walking forward. Okay, it's a lot of information. Any questions? I'm just going to pause for a moment and take any questions if there are any. So far, so good? Okay, I'm going to unpause the video. You're going to see the next robot is the blue robot. I want you to type in BY. We're going to actually play Twitch Plays Robotics here for a moment. In Teams chat, I want you to type in BY if you think the blue robot is walking forward, or BN if you think the blue robot is not walking forward. One vote BN, one vote BY, one vote BY, 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 BN, BY, 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 BY. Okay. All right. So at this moment in time, we have, okay, I'm not going to count it up, but we've got quite a few votes here. I think it looks kind of split. Maybe a couple more votes. Oh, maybe it's split. Half say yes, half say no. Okay, so we now have one data point, which is for this particular robot, the blue robot, which has one random controller. We have one random controller for that robot. We have the symbol. We have the symbol walk forward. We have the symbol walk forward, and associated with that command is a bunch of yes votes and no votes. So we played this task over and over again, and over the course of a few weeks, we had hundreds of people label thousands of random controllers for hundreds of different commands. Okay, so this is the act part of the process where we're generating a large data set, which is being stored in a database. Okay. What does this data set look like? You just generated some data, so hopefully you start to have an intuition for what this data set looks like. In this particular project, we actually used two different robots, which you probably noticed in the video. There was the quadruped robot, and then there was the simple worm robot. So R0 is the worm, R1 is the quadruped. So R0 and R1, two robots. So R sub I is going to represent the ith robot. I equals 0 is the worm, I equals 1 is the quadruped. For each of these robots, the crowd generated multiple commands: walk forward, spin, stay still, and so on. Each of these commands is going to be represented with two subscripts, I and J. So C sub ij represents the jth command issued to the ith robot. So C03 is going to represent the third command sent to the 0th robot. Okay. For each of these commands, and these commands were issued multiple times so the crowd can vote, they sent walk forward to the robot once. Later, they sent walk forward to the robot again. So each of these commands, it would be, every time this command was issued, there'd be a different random controller running on the robot. So we're going to represent the controller with an N. The N's are now going to have three subscripts. Nijk is going to represent the kth controller evaluated under command J. So this was the kth controller was controlling the ith robot. I'm sorry, I forgot to put the robot I here. Controller K was running on the ith robot when the crowd issued the command J to that robot. Okay, so we got R's, C's, and N's. For one of those N's, like the one that you just saw running on the blue robot, let's assume that that controller running on the blue robot is Nijk. We got a number of positive reinforcements. Positive reinforcement. This is good dog, good kitty. Positive reinforcements are all the yeses. I can't sum them up here, but there may be about 8 or 9 or 10 yes votes. So Sijk, 1 is the positive, 0 is negative. So Sijk1 in this case would equal 9. There were 9 yes votes for this particular command when this particular robot was being controlled by this network. Okay, this is a lot of notation to introduce. I'll just give you a moment for that to sink in. Sijk0 obviously is the number of no votes. So for each controller, there are two integers associated with it, two positive integers associated with it, the number of yes votes and the number of no votes. Okay, so that's the second phase, the observation phase. So after the Twitch stream shut down, after a few weeks, this is what we had as a result. In this very first Twitch Plays Robotics project, the robots were not evolving or learning as the crowd was talking to them. Here we're going to do some offline learning, which means the robots are going to learn to ground these symbols after they've heard it. This is just this makes things simpler from the coding point of view. This was our first attempt. Okay. Any questions about this data set or anything about TPR before we push on? There's a lot of moving pieces in this experiment. So far, so good? Okay. Okay. So let's just have a look at the data we actually collected. As I mentioned, we ran this project for a couple of weeks. During those couple of weeks, we had 424 visitors to the stream. These are our human subjects. Our human subjects, in order to qualify for this group, they typed at least one thing into chat. If you spend any time on Twitch, you'll know that there's usually much more lurkers, people that watch the stream but don't type anything into chat, than there are active participants. These are active participants. Over that 2 week, I think it was a 2 week period, 57,000 robot evaluations were performed. We ran 57,000 simulations. In each simulation, we evaluated one random neural network controller. So we evaluated 57,000 random controllers. Most of these were simulated while there was no one on the stream. So we reduced this number to, I think it's 6,388, that there was someone actually watching the stream at that time. And we collected over that 2 week period over 16,000 pieces of chat. So inputs are just the subjects typed something into chat. What did the subjects type into chat? We got nearly 9,000 unique pieces of chat. And if that piece of chat had the form BY, blue yes, or violet no, we knew that those were reinforcement signals. Those are a special piece of chat. Anything else that people typed into chat, like jump up, what's the robot doing, jump, go forward, all of these were considered commands. You'll notice that what's the robot doing, that's probably not a command, that's just the user not knowing what this stream is about. So our net captured some commands that probably weren't actually commands. Among these almost 9,000 pieces of chat that were not reinforcement signals, these pieces of chat did not have the form VY, VN, BY, BN, and so on. There were 266 unique strings that were typed in. So what that means is obviously a lot of the commands that were typed in were repeats. It turns out that the command that was typed in the most number of times was jump. 385 times. The second most popular thing typed in was walk forward, move forward, run, crawl forward. We told the crowd they could type anything into chat. What's interesting is that the most popular, the top 5 commands typed into chat are Motoric commands. Among this set of 266 distinct things, people, you can imagine people on Twitch type in all sorts of things. Obviously, swear words was pretty high on the list. This experiment was carried out in 2015, before a lot of the abuse filters were put on Twitch. So we captured a lot of bad words. But hey, if someone's learning a language, what do you usually try and teach them first? It's the swear words. So I guess that wasn't too far out of the ordinary. We had one user who commanded the robot to prove Fermat's last theorem. Probably not something that the robots are going to be able to ground in felt experience anytime soon. We had someone type into chat, be yourself, which is kind of an interesting one. That's either a very, very abstract command or possibly a motoric command. How can a robot or a human not be themselves? Someone else typed in the command, look at the camera. That was actually a good one, but probably not something that the robot was going to be able to ground in its own felt experience. Okay, so this was the experiment was already kind of a success because it shows that people are instinctual teachers. When they see these robots, even though we don't tell them there's a random neural network controller, they can sense that these robots are kind of helpless or not really capable of much. So the teachers on Twitch, that are typing into chat, they simplify what they ask the robots to do, presumably in the hope that the robots will be able to ground that simple language. And then once the robots ground that simple language, maybe the chatters can start to issue increasingly rich and complex language to help the robots back up again. What is that process called? It's a very common process seen among all kinds of teachers and parents and animal parents as well. We've talked about this idea before. What is this mechanism of simplifying language or simplifying the learning process for the learner until the learner can grasp the rudiments of what they're being asked to do and then start to become better at it? It's a concept we've seen a couple times already in this course. We have a teacher or parent that's trying to make things easier on the learner. And then once the learner starts to signal competency, we're going to remove some of that support. What's that idea? I'm actually doing it right now by giving you all these verbal hints. But it seems maybe they're not sufficient for this morning. No ideas? You may remember our discussion about scaffolding, right? Making things easier on the learner. You have a parent, and that parent will place their child's feet on their feet, and the parent will then walk, and that will move the child through the experience of walking. Once the child starts to walk, we remove that scaffolding. This is another example of scaffolding or spontaneous scaffolding. We didn't tell the Twitch chatters to go easy on the robots. They spontaneously did it on their own. And this is part of the reason why we're trying to recruit non-experts to teach our robots through Twitch, is that people are instinctual teachers or instinctual parents or mentors, whether they know it or not. Kind of an interesting twist on this project. Okay, let's carry on. The reinforcement signal, so we got over 7,500 pieces of yes or no, which are the S's here. And the proportion of positive reinforcement, I'll talk about O in a moment. The actual value doesn't matter. But mostly people typed in yes more often than they typed in no. Kind of interesting. Okay, so now we're going to see, given this data set, can we get the robots to actually learn anything? Can the robots discover a relationship between a given symbol issued by the crowd and the robot's own felt experience? I mentioned that the robots were run using a random controller. So what we did was to replay a subset of the ends, a subset of the controllers. But in this case, we're going to record sensory information. We're going to record the robot's felt experience and see if there is a relationship between that felt experience and the command. Okay. We focused on just one command, one of the C's, which was jump. Jump was issued 385 times. So we took all of the controllers that were executed on the robot while the crowd had issued the command jump. So we're just going to focus on seeing whether we can find a relationship between sensor values and jump. Okay. How did we do this? You'll see here in this case we have the simple worm. The worm is made up of just 3 pieces, 1, 2, 3. We put 3 touch sensors in this robot in each of the 3 links that make up the robot. We replayed the first random controller issued to the robot under the command jump, and we recorded sensory information generated by that random controller, and we placed it in a 3 by n matrix. Each row corresponds to 1 time step in the simulator. In this example here, the random controller caused the middle link to be in contact with the ground, and the front and back link were off the ground. So this first row corresponds to the values of the 3 touch sensors in the first time step. Here's the value of the touch sensors in the second time step, third time step, and so on. So we now have jump. We now have a matrix which represents the sensory information. We did that for all of the random controllers issued under the command jump. And then among that set of random controllers, we reduced that set to just the set in which the S's, the sum of the two S's was greater than 0. What I mean by that is we recorded just those random controllers in which people typed at least one reinforcement signal, at least one yes or one no, into chat while that random controller was controlling the robot. So far, so good? Okay. Oops, sorry. Okay. So here's one of these random controllers issued on the robot under the command jump. We now have a matrix T, which is all the touch information. And remember, we also have associated with this random controller S0 and S1, the total number of yes votes, S1, and the total number of no votes, S0. We're going to take these two values and we're going to normalize them into a new value O, which is the crowd response. And this value O is going to range between -1 and +1. An O of -1 means there was unanimous negative reinforcement of that controller. An O equal to 0 means there was an equal number of yes and no votes. Sorry, -1 is unanimous negative reinforcement. An O of 0 means half yeses, half nos. And an O of 1 represents unanimous positive reinforcement. So you all typed in about an equal number of BN and BYs. So that particular controller that you were voting on probably would have got an O near 0. So far, so good? Okay. Let's have a look at some of this data. Each of the points here corresponds to one of the several hundred random controllers that was run on the worm robot when the crowd issued it the command jump. You can see each point here representing each of these random controllers. The vertical axis, or the height of each point, represents the normalized reinforcement signal. So how many yeses versus how many no votes did that controller get under the command jump? The horizontal axis here is the proportion of time that the robot spent on the ground. That's a calculation we can do using the T matrix. We visit each row in the T matrix, and if there are 3 zeros in that row, that means the robot is off the ground. If for a given row there is one or more ones, that robot is grounded. It's on the ground. So we can calculate by going down that row, what's the percentage of time that that controller caused the robot to be grounded, to be on the ground. Okay. So let's pick a couple points here. Let's pick this point over here. The horizontal position is at about 0.48. So this robot spent 48% of the time grounded and 52% of the time off the ground. So this robot was airborne most of the time. But interestingly, it got unanimous negative reinforcement. The crowd thought this robot was not jumping. Kind of doesn't seem to make a lot of sense, this one, but so be it. Let's pick this one over here. This controller over here spent caused the robot to spend 97% of the time on the ground. And there was, it had an O of about 0.3. So it was almost split, but there were slightly more no votes than yes votes. If you look at the distribution of all of these points, it's not a perfect relationship. It's pretty messy, but generally speaking, most of the points are up and to the left, and most of the points down here are down and to the right. Points that are in the upper left here, these are controllers that cause the robot to be mostly airborne, and for which the crowd unanimously said the robot is jumping. Down here, these are controllers that cause the robot to be mostly grounded, and the crowd unanimously said, no, the robot is not jumping. If you take a straight dotted line like you see here, and you try and place this straight line in the two-dimensional plane so that this dotted line is as close as possible to all the points, you get a negative slope. This is linear regression. Linear regression attempts to find patterns in data. Obviously, these points do not line up along this line, so it's not a very good fit, but it's a good enough fit for our purposes. This line, the slope of this line, represents the robot's understanding of the command JUMP. The robot knows that if it spends more time on the ground, the robot is going to get more no votes. And if the robot spends more time in the air, it's going to get, on average, more yes votes. So the understanding of JUMP from the point of view of the robots is actually the robot stitching together multiple pieces of information. These pieces of information have to do with the robot's body. They have to do with the robot's experience. How much of the time do I spend on the ground versus off it? It has to do with a social relationship. The robot, maybe it doesn't know that there are humans out there, but it knows about this signal. There is some signal coming in from outside that is related to this signal over here. So there's also a social component to this. So the robot's understanding of JUMP connects body, felt experience, social reinforcement, and the command itself. We've got 4 minutes left, so I'm going to just finish up with this picture here. I mentioned we used 2 different robots in this experiment, the worm and the 4-legged robot. This 4-legged robot has 4 touch sensors in each of the 4 legs, so it has a slightly different body. And when we run a whole bunch of random controllers on this robot, it has a slightly different felt experience than the worm robot. If you just pay attention to the horizontal distribution of these points, you'll notice they're a little bit different between these 2 robots. Both robots are trying to ground the same symbol, but they have slightly different physical experiences, and they have slightly different social reinforcement of those experiences or of those controllers. If we take a straight line and we try and fit it to this data, for this particular robot, we again get a negative slope. But I'm going to go back and forth again between these 2 slides. Have a look at the 2 dotted, or have a look at the 2 dashed lines in both of these images. You'll notice they have very slightly different slopes, and they also have slightly different y-intercepts. If we're representing this dashed line of the robot's understanding of the word JUMP, or the symbol JUMP, this finding suggests that the word jump means slightly different things to these 2 robots based on the slightly different bodies and the slightly different experiences of these 2 robots. This is kind of an unexpected result, maybe expected in retrospect, but it wasn't expected to us when we started this project, that if you're going to use your body to ground the symbols of language in the soil of sensor motor experience, if your body is different, you're going to ground those symbols slightly differently, and those words are going to mean slightly different things based on your body. If we want to teach robots language, Maybe that will be more or less difficult if the robot's body is more or less different from human bodies. Would this robot ever understand what look back in anger means if this robot spends half its time moving backwards and half its time moving forwards? Probably not. If this robot, because it looks forward, if this robot looks forward and moves forward most of the time, then there is a hope, at least, a potential that it might be able someday to understand the metaphor, don't look back in anger. The little googly eyes that we put on this robot in this very simple experiment, it doesn't actually have eyes, it doesn't have infrared sensors, it doesn't have cameras. The eyes there are just meant to help the users understand which is the front and which is the back of the robot. The robot also doesn't experience anger. So looking back, exhorting the robot to not look back in anger, who knows? Okay. I think we'll stop there for today. That's a lot of information. There's one quick question from Logan. Go for it, Logan.
Yeah, I just wanted to go back and ask about the point that you were making, because it seemed like it was kind of important about how we teach and how that relates to what we're teaching. So like it would be easier for us to teach something that has a similar body to our own. And I was just curious then how, people can train their dog, or they can train, another animal that's not quite similar to them, but they're still able to go and get them to act in such a way.
That's a great question, right? How do we teach our pets? Our pets have different physiologies from us. What commands do we teach our animals, and what do you think they understand about those commands? I'll leave that for the pet owners to think about. It's a very good question, Logan. We're out of time for today. You have a quiz due tonight. You're working on deliverable 3, and we'll see you all back here Thursday morning. Have a good day, everyone. Bye-bye.